Hello everyone. Here we have a sample problem for MEC 375, mechanical vibrations. And in this problem here, we see that we have a forced vibration problem because we have this input with this sinusoidal curve here. Now, what they ask us for in this problem is to find the equation of motion, find the steady state displacement of m, and to find the force transmitted to point P. Now, for any mechanical vibration problem, we always want to start with the free body diagram. And this is useful in finding the equation of motion. So here we have mass m. And if I look at the forces, we're going to have the inertial force to the left. We're also going to have the spring force based on K2 to the left, and we'll have C2 to the left as well. But then when it comes to C1, I'm going to also put it towards the left to make this easier. So this one will give us mx double dot. This will give us C2x dot. This will give us K2x. And this will be C1 times the relative displacement between y and x. So since I know that this one's dependent on x, I'll put x first. And this only works if this arrow is following the same direction as all of these. So what I need to do next is I need to get the modeling equations, which basically comes down to applying Newton's law. So we have mx double dot plus c1 plus c2 x dot plus k2x is equal to c1 y dot. So this is from your basic force balance. So this finishes the first part of the problem where we have to find the modeling equations, which we have already found. Now, what we're interested in finding is the steady state displacement of mass m. And the variable attached to m is x. So we want to find the steady state variable value for x. So in order to do so, we need to make a replacement where x is equal to x e I omega t, and let's say y is equal to y e I omega t. So these values here stand for that steady state value. So if I were to take the derivative of these, so x dot, this will give me I omega x e I omega t, and x double dot will be minus omega squared x e I omega t. This will give us y dot is equal to I omega y e I omega t, and y double dot is equal to minus omega squared y e I omega t. So this is going to be the replacement we're going to do in this problem. And we're going to take these equations and basically plug them into our equation over here. So plugging these into this equation, you're going to notice that all these e I omega t in this equation, they should cancel out. So let's completely ignore the e I omega t. So this equation will end up becoming minus m omega squared x plus c1 plus c2 omega, sorry, I omega x plus k2x is equal to I omega c1 y. So here's our equation. And now what we want to do is basically isolate for x, and we're going to get the steady state value for x. So basically cleaning up the left side of the equation, here we have k2 minus m omega squared plus I omega c1 plus c2 x is equal to I omega c1 y. So now isolating x, we get x is equal to I omega c1 y all over this guy here, which is k2 minus m omega squared plus I omega c1 plus c2. So we have the steady state value for x, but the thing is, if you notice in these equations, we have all these imaginary values. So this becomes a problem, but we can make this nice for us by just taking the magnitude. So we need to recall, for these types of problems, imagine here we have our imaginary axis and we have a real axis. So this is our real, This is our imaginary part. And imagine here we have some vector as such. So this vector here has some imaginary part, and it also has a real part. So to find the magnitude of this vector, basically, let's say we'll call this A. So the magnitude of A is equal to the square root of the real squared plus the imaginary squared. So this is going to be the technique in figuring out how to solve for the value for x without all these imaginaries. And if you want to find out how to solve the rest of this problem and applying this rule over here, you can come visit us at Gradesavers and come visit our crashes and weeklies, and we'll show you how to solve problems like these and other problems that has to do with mechanical vibrations.